as we've been looking at the sorting algorithms, we've seen that they're starting to divide themselves into categories. Those sorting algorithms that are n-squared algorithms and those sorting algorithms that are n log n. In practice, we want to make sure we're using n log n sorting algorithms, and the algorithms that are built into most modern programming languages, Java included, have as an underlying implementation a QuickSort or a merge sort operation. I want to introduce QuickSort. QuickSort is also an example of a divide and conquer algorithm, also has a running time of n log n, but it's slightly different, and its algorithm is a little bit different. And the way that it differs from merge sort, and one of the ways that it's stronger than merge sort, is it doesn't require any temporary arrays to move things from A to first and second or first and second to A. And this is convenient and it's helpful because what it means is that we're able to we don't need twice as much memory as the array that we're currently sorting. We can sort things with the memory that we're given. Also divide and conquer algorithm, we're going to partition our a given range of our array, and then we're going to sort each partition in place. So in QuickSort, you partition these elements into two groups, and you keep the smaller and larger elements as an index, and then you sort each individual subgroup. So let's take a look at what this looks like. When we sort, we're going to keep track of, rather than a particular array that we're sorting, we're going to keep track of a from index and a to index. These are the beginning index and the end index of an existing array that we're going to sort. And so as long as from is before 2, meaning from is earlier than 2, because we're talking about indices in an array and we want from to be earlier than 2, because we want to be actually sorting an array that has content, we don't want it to be flipped. Our base case is when from and to become the same, meaning we've got a little chunk of data that has no elements in it, and so we're going to return. But if we do have some data between from and to, then we're going to partition those two elements. Then partition gives us a value, gives us a position in between, an index p, between from and to. And then we're going to recursively sort on the piece below and the piece above. And in that way, we're going to end up sorting our entire array in place. So let's take a look at that. Our starting range, for example, might be an array that is 5, 3, 2, 6, 4, 1, 3, 7. It's an unsorted array. And so when we partition, what we're going to do is we're going to pick a position in the middle, and we're going to move everything that is less than that position to the left of the partition, and everything that's right of that partition to the right of the partition. But we're not going to sort each piece. We're just going to say that each piece is higher than the partition element that's present. So in this case, what we're going to do is we're going to find an element that's about the middle. And so that's the 4. We're going to say 4 is our partition element. And so we're going to go through every element of the left side and the right side. So we're going to start at 3 and we're going to start at 6. And we are going to swap out elements so that we are sure that each of the left side and the right side are, if the left side is less than 4 and the right side is greater than 4. And then we're going to recursively partition on each smaller piece in turn, so that we don't have to do a merge step, because it's like we're front loading the merge step. Instead of merging at the end, we're swapping things to the left and right. And we continue breaking down these little pieces to the left and right until we get down to a partition that is, just one element, so there's no swapping. And so then when we go back up, each of our smaller partitions has already been sorted, and before we recursively called those, we know that they had been separated into things that were higher and lower than our partition. So it's kind of a reverse of merge sort. We first do a split, and then we recursively solve and sort the subarrays. All right, so it's just a clever way of doing a divide and conquer algorithm that doesn't require us to have a separate array. Our partition algorithm then does a little bit of that front-loading work. It takes in an array that we want to sort. It takes in a range that we want to partition from. It just says, okay, randomly picking what we're going to partition, we'll just take the first element of our range that we're sorting and say that's going to be our partition. And then what we do is we take two indices, I and j, and as long as I is less than j, we're going to increment them. And as long as the elements in our array are less than pivot, we're going to move our left side forward. And as long as the elements in our array on the right side of pivot is greater than our pivot, we're going to move our left side left. So we start at one side and we move them in, swapping elements if necessary until we get to a position that's the same. So we put our indices at the end, we walk them in, swapping elements if necessary until we get to a point where I and j are the same. So they're indices that are walking together. What this looks like is something like this visually. We have our index from and to, that's the beginning and the end of the section of the array that we're interested in sorting. We have I and j, that I initially starts as from and j initially starts as to. And then as we loop, we bring I and j one closer, swapping them if they're greater than or less than the partition. So at some point in the middle of this partition algorithm, it looks like the top diagram here, where the outside edge has been pivoted so that it's greater than the partition on the pivot on the right and lower than the pivot on the left, but the components in the middle haven't been analyzed yet. And so we gradually move I and j together until they are the same, and we know that the right side and the left side are both greater than or less than the pivot. On average, like merge sort, QuickSort is also an order n log n algorithm. The reason why we say on average is because there is a way to arrange an array so that QuickSort has very bad behavior. Because of the way that we choose that pivot, if we choose that pivot poorly, then the worst case runtime behavior of QuickSort is the same as selection sort, order n squared. And that's if you have kind of an adversarial pivot selection. One way that you can avoid this is, well, you can't avoid it for sure, but you can, if you know that your data is arranged in a poorly formatted way, you can shuffle your data before you try and quicksort it, which is sort of counterintuitive, but it ensures that you don't have a degenerate behavior. It doesn't guarantee it, but it makes it very less likely. Okay, so that's the quicksort algorithm. It is used in practice. It is kind of the default algorithm in many cases because it is as effective as any divide and conquer algorithm, but it doesn't take up any more memory. Thank you for your attention.